Hello there, welcome to my channel on Chemistry Lessons. This is BTEC Applied Science and it's Unit 5 Chemistry, and we're going to be looking at the June 2018 paper. So there it is. So at this point in 2018 they decided to split the exams to 3 separate exam sessions. You may have noticed that earlier exams it was actually all 3 back to back to back, and now they put them over 3 separate sessions. You've got so this would have been Tuesday the 5th of June and you were given 50 minutes to do this paper. First up though, if you don't subscribe, please do. Your support is very much appreciated. Please take advantage of the likes and comments features. Let me know what we think. So how I suggest you do this is I suggest that each question I'm going to ask you to pause, and that gives you a chance to pause the video, have a go yourself, and then when you're ready to hear the answers you can unpause. What I do suggest you do though, if you haven't done your revision, you need to check out my playlist first, and I'll put a link across the top now for you to check out the playlist for the full Unit 5. So the first couple of marks are multiple choice here. First up, methane has the form CH4. What is the correct bond angle? All right, well, the bond angle in alkanes is 109.5 degrees. There we go. The bond angle in alkenes was 120, and in benzene it was also 120. So there's my first mark there. Second multiple choice, give the IUPAC name. Right, okay, well, how many carbon atoms? 1, 2, 3, 4. Remember, I can number it in reverse as well. 1, 2, 3, 4. So it's butane. So I can ignore C and D because they say pentane. Right, now I've got to go with the lowest number. So this is in fact 2 bromobutane. It is not 3 bromobutane. So be careful there. And the final 2 marks for this. So methyl propene reacts with bromine. Yes, I know it does. There was several reactions we needed to know. This was one of them. What happens here is it adds across the double bond, so the double bond breaks and we end up with a bromine here and a bromine here. So let me draw that out. So the carbon on the left will now have 2 hydrogens. Don't worry where you draw the hydrogens. You can put them in any order. As long as this carbon has 1 bromine and 2 hydrogens, I can put them anywhere. The carbon on the right has a CH3, another CH3, and a bromine. So there's 1 bromine on each of them. That really doesn't look like a 3, but it is there. And that's worth 2 marks. Next part then, so the rest of question 1, and this is the final 6 marks. As always, pause the video, and when you're ready to hear the answers, unpause. Well, the type of reaction, well, that was the electrophilic addition. So the reactions, electrophilic addition. So it's the electrophilic addition reactions of alkenes. 2 marks, electrophilic addition. I get 1 mark for the word electrophilic and 1 mark for the word addition. Which row shows the correct number of sigma and pi bonds? Right, well, I know that a double bond is 1 sigma and 1 pi bond, so the answer is C. Living my best life right here. Explain how the carbon-to-carbon bond strength in ethane is different to the bond strength in ethene. Okay, so ethene is just a sigma bond, and ethene is a sigma and a pi bond. So explain how it's different. So I'm going to make the statement that the bond strength in ethene is greater than the bond strength in ethane, because ethene contains a sigma and a pi bond, and ethane only contains a sigma bond. The sigma bond is a shared pair of electrons, and ethene will have 2 pairs of electrons due to the sigma and the pi. If I was to say any more, I'd start waffling, but any 3 of those points. Question number 2. Lots of information here. As always, I suggest you pause it, have a good read, have a go yourself, and when you're ready to hear the answer, we can unpause it. Okay, so this is all about the electrolysis of brine. And yes, the diagrams may differ from time to time from the ones in my video and the ones that you'll see in revision guides, etc. But the information will all be on that diagram. Okay, so I know that chlorine and hydrogen are made, it's telling me that. I know that sodium hydroxide is also made, but I can see that in the diagram. Let's answer the question. At the cathode, hydrogen gains electrons to produce hydrogen gas. I knew that anyway, because I'm a smarty pants. At the anode, chloride ions lose electrons to become chlorine gas. Chloride ions lose electrons to become chlorine gas. Yes, they do. I need 2 chlorides and I'll have 2 electrons. There we go. Done. 2 marks for that. Next part then is worth 4 marks. They're asking us to explain the function of the membrane. So again, suggest you pause, and when you're ready to hear the answer, unpause the video. Okay, so you don't have to list all of these things, but when we looked at the membrane, that was to, first of all, allow the sodium ions to flow, but the chloride ions could not. Okay, so the sodium ions can pass through the membrane, the chloride ions can't, and that means that the sodium hydroxide is not contaminated with the chloride ions. And also it means the chlorine won't be able to react with the sodium hydroxide. It also keeps the gases separate. Okay, so any 4 from that list is going to get you the marks there. Quite a tough question, that one. Moving on to question number 3. Transition metals are often used as catalyst. Explain how a transition metal works as a catalyst. So as always, I'm suggesting that we pause the video, and when you're ready to hear the answers, you unpause the video. Okay, so there's quite a bit we could write for this. It's only 3 marks. So what I'm going to say is a catalyst speeds up the rate of a reaction by offering an alternative reaction pathway with a lower activation energy. There's a few more things you could say, but I've mentioned 3 things there. It speeds up the reaction by offering an alternative reaction pathway with a lower activation energy. Part B. So we've got a complex here. Describe how the water molecules bond to the vanadium. Well, what happens here in any transition metal complex, this water is classed as a ligand. I don't need to use that word here though, but that's classed as a ligand. What happens is there's a lone pair of electrons on the oxygen in this case, because it's the oxygen that's bonded to the vanadium metal. There's a lone pair of electrons on the oxygen that are donated to the vanadium to form a bond. Here's your mark scheme. As you can see there, 3A, there's quite a few different things you can say, but I mentioned those first 3 and that was fine. 3B, we have to say that there's a pair of electrons on the oxygen and they've been donated. In Unit 1, you did actually see this is a dative covalent bond, so I could mention that, but it's not essential. As long as I've mentioned there's a lone pair of electrons on the oxygen that can be donated. And that comes from the oxygen to the vanadium. Question number 4. Pause the video, unpause when ready for the answer. So propane is an alkane and has the formula C3H8. Give the general formula for an alkane, right? The general formula for an alkane is CnH2n plus 2. 1 mark. Balanced equation to show the cracking of propane. So we know that propane is C3H8. We know that cracking is breaking the chain into shorter chains. So we're being told we're going to produce ethene. Now we need to know that ethene is an alkene with 2 carbons. So that's C2H4. So that's ethene. And now I'm going to do a little bit of maths to work out what the other product must be, because it says 1 other product. Well, I've only got 1 carbon left because I started with 3 carbons on the left. So my other product must have 1 carbon, since the other 2 carbons are in ethene. So it's C. How many H's have I got left over? Well, we started with H8 and we've got 4 in ethene. So this must be CH4. Done. A catalyst can be used instead of steam in the cracking process. Steam provides a higher yield of alkenes than using a catalyst. Suggest 2 benefits of using a catalyst to crack hydrocarbons. So this question really, it's not so much about cracking, it's asking us to explain the benefits of catalysts. So catalysts, they speed up reactions. They allow reactions to take place at lower temperatures, which reduces the need for heat and reduces running costs. I'll show you the list here. Here's the mark scheme. You see here, there's quite a long list. We can use low temperature, I mentioned that. It produces more product in less time, conserves energy, I mentioned that one. Higher yield, you can reuse a catalyst. So there you go, any two valid points there. Question 5 up next then. You know the drill by now. Pause and unpause when we're ready. Okay, so this question's about an enthalpy change, specifically enthalpy change of combustion here. And we're being asked for the definition first off. So definition is enthalpy change when 1 mole of a substance completely reacts with oxygen under standard conditions. I'm going to show you the mark scheme shortly. Part B, enthalpy change of formation is measured under conditions of 1 atmosphere and 298 Kelvin. Give the temperature of 298 Kelvin in degrees C. Now, we need to know how to convert between the two units. To go from degrees C to kelvins, you add 273. Therefore, to go the other way, you minus 273. So my answer is 25 degrees C. There's our mark scheme there. This question's a large 5-mark Hess cycle calculation. If you haven't seen my video on Hess cycles, I strongly suggest you do go and watch that first, and then you come back and have a go at this, because these can be really easy, simple 5 marks to pick up. So as always, pause the video, and when you're ready to hear the answer, unpause. Okay, so my advice here is to get this into a nice triangle with 1 unknown and 2 knowns. Our unknown in this case is the enthalpy formation of butane, which is the arrow across the top. So we should have information in this table to allow us to put a value on the right hand side and a value on the left hand side. The value on the right hand side is just the combustion of 1 mole of butane. So this one is quite straightforward. This is the enthalpy of combustion of 1 mole of butane, which is given in the table. The standard enthalpy of combustion of butane is minus 2876.5. The arrow on the left is a little bit more complicated because it's the combustion of carbon and the combustion of hydrogen. And specifically, it's 4 moles of carbon and 5 moles of hydrogen. So this value here needs to be times by 4, and this value needs to be times by 5. So it's 4 times carbon and 5 times hydrogen. If I do that and combine them together, I will get a value of minus 3003.8. Check that on your calculator. 4 times minus 393.7 plus 5 times minus 285.8. You will get minus 3003.8. Now, my next step is to come up with use Hess's law. My start point is here, my finish point is here. So my root 1 is equal to x. I always make my root 1 my unknown value. And root 1 is equal to root 2. Root 2, I've got to go this way around the circle or the cycle. So it's the same direction as this arrow, which is minus 3003.8. But this time I'm going against this arrow. Look, I'm going in the opposite direction. So this, instead of being minus 2876.5, it becomes plus 2876.5. It's a bit messy. Combine those two there, and I end up with an overall value of minus 127.3. And since root 1 is equal to root 2, that is my value for x. Minus 127.3. Units are kilojoules per mole. Here's the mark scheme. As you can see, correct answer is minus 127.3. This is the final question on the exam now. Finish with 6 marker. That's normal. It's quite normal for an exam to finish with a 6 marker. So read the question, give as much information as you can, and when you're ready to hear the answer, you unpause the video. Okay, what we're looking at here then, so we've got enthalpy profile diagrams for two different reactions. So I'm just going to explain as much about them, but it's saying the differences. So I've got to talk about the differences. The first obvious difference is reaction 1 is exothermic, reaction 2 is endothermic. Reaction 1 is releasing energy to the surroundings, reaction 2 is absorbing energy from the surroundings. What else can I identify on these profile diagrams? I can talk about the activation energy. Now the activation energy for the one on the left is less than the one on the right. This is the activation energy. I've probably said enough for 6 marks, but here's the mark scheme. Let's have a read through it. You could have gone into talking about bonds being broken, bonds being made, as you can see. There's an awful lot you can say there, but you don't have to hit all of those points. That's the beauty of it. You can just talk about a few of them from each of them, and that's going to add up to our 6 marks. And that's that paper completely finished. So thanks for watching, and don't forget to subscribe, use the comments features, let me know what we think, and good luck in your exams.